guys. So the first question in the workshop is define the following terms: kinetic energy, potential energy, thermodynamics. So that's easy enough. But I guess the next part of the question is give an example for parts A and B that you can demonstrate safely in the classroom. Be creative. So I want them to not only define kinetic energy and potential energy, but be able to take whatever is around them and be able to give an example of kinetic energy and potential energy. And the basic one that you guys can do is just the eraser. So as I'm holding the eraser, here we have potential energy. Okay, we have stored energy in the eraser. If I move it higher up, we have greater potential energy, greater stored energy. If I move it down, we have less stored energy in the eraser. Okay? But the idea is stored energy converted into kinetic energy, the energy of motion. So when I drop it, oh, there we go. We have kinetic energy. Okay? The energy of motion. Okay? And that's just a basic demo that they can do in class. But the idea is for them to do the demo so that they can visually see the demo, perform the demo, and hear other students explain the demo so that they can make that connection to that particular question on the exam. So that's kinetic and potential energy, and they should also be able to define the basic concept of thermodynamics, which is essentially the branch of chemistry that is concerned with the changes in energy, the energy changes, okay? And one major concept that you should ask them about is where we find different sources of energy. So you have solar energy, you have magnetic energy, etc. And ask them what do they all have in common, which is exactly what I did at the prep meeting, okay? So those are one of those extra questions that you can ask your students. So with that, what they all have in common is essentially that they're all we're able to convert all of the different sources of energy into the common unit of heat. Okay, which the kilocalorie or the joule. Okay, the joule, which is typically used in physics problems. Okay, and that's problem number one. So question number two, we have all activities in living organisms involve changes in energy. A set of universal laws govern all energy changes from nuclear reactions to stressing out before your biology exam. What are these universal laws? So we have the laws of thermodynamics. We have the first law and second law of thermodynamics. The first law of thermodynamics is that of the conservation of energy. Energy cannot be created or destroyed. The second law, which is the law of entropy, the universe progresses towards chaos. So I give you guys examples on the workshop for them to define which one's the first and which one's the second law of thermodynamics. But again, you're not telling them these things. You want to ask them. Okay, so you want someone to tell you the first law, someone to tell you the second law, and other two people to decide whether it's the first and second law and to explain it. Again, you want them to get to say the information versus you guys telling them the information. So the following are examples of these laws. Explain which law the example falls under. Part A, plants pick up light energy from the sun to perform photosynthesis, where they use it as chemical energy. So here you have the conversion from light energy to chemical energy. So you have the conversion of one form to another. You didn't lose nor create the light energy or the chemical energy respectively. So this is referring to the first law of thermodynamics. Part B, a droplet of red dye spreads through the water-filled beaker until the entire beaker has turned the color red. So the idea of diffusion itself leads us to the second law of thermodynamics, which is essentially the law of chaos, the law of entropy. Okay. And again, you want to get that basic information out of your students. Okay. And that's question number two. So as you can see on the board, here we have the equation for Gibbs free energy. So here delta G, the Greek symbol delta, when we're talking about the mathematical sense, will always represent change in the variable that it stands next to. So here the change in the variable G. The variable G is the Gibbs free energy. So delta G would stand for the change in Gibbs free energy. Okay? Now, that equals delta H minus T times delta S. So the change in H, the change in S. Delta H is the change in enthalpy. T represents temperature in Kelvin, not degrees Celsius, not degrees Fahrenheit, in Kelvin. Then delta S stands for the change in entropy, the change in chaos. Now, the problem proposed is calculate the change in Gibbs free energy when the ice cube melted using the data table in the table below, the data in the table below. And you're given the equation as well, delta G equals delta H minus T times delta S, along with the data table, which is basically summed up right up here. So, essentially you would just plug in the numbers. You want it in the melted temperature, so you need the T80 as your temperature that you're going to plug in. The change, however, in enthalpy, you would need the change here. So 100 minus 50 to get the value for delta H. To get the value for delta S, it would be 20 minus 5, 15. So here you would have 50 minus the temperature, 280 Kelvin, times the change in entropy, which is 15. Okay? You calculate that, and that will give you a certain number. And so you would have the positive delta G or negative delta G according to your numbers. So whichever one it comes out to be, whether positive or negative, if it's positive, then in that case you would actually not have a spontaneous reaction. If it's negative, then you have a spontaneous reaction, and your students should be able to discuss the differences between the two. Okay, whether it's spontaneous or non-spontaneous, and what that means according to essentially the laws of thermodynamics. Okay, and again, the idea is to get as much out of your students as possible. Literally grab the information from the students. And the first session might be a little bit difficult because they're not used to it. So, literally, just as best you can, get that information out of the students versus you guys actually telling them. Throw people on the board, have them do it on the board, really put them on the spot and make them do all these things. Okay?